For this video, I will discuss to you the Heine-Borel Theorem. Now, it is one of the most important properties of a closed and bounded interval. Now, here we consider a class. We have here a class set A. It is said to cover a set A if A is contained in the union of the members of the class. So we have this notation here for the containment of A in the union of the class of sets. So let's have this illustration. So let's consider the class of sets. We have here A1, A2, and so on. So we have here A sub I, where I is a natural number. So let us try to consider this set. Say this is our set A here. So let us try to assume that this is our A1, this is A2, A1 is somewhere here in the set. Say A2 is here, then A3 is here. So we have here A4, say A4 is here, now A5 is here, then A6 here. So we have A7, we have A8, A9, and so on. So that's it. Now we can say that this class here, ito siya, covers the set A. As you can see, it covers the set A. Ito. So we call this class as a covering of the set A, or this class is a cover of the set A, or it covers the set A, as you can see in the illustration. So we call it as an open cover. The class is an open cover of the set A if each of the interval here is open. Say this is open, 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 and so on. So again, we call the class as an open cover or cover if the set is contained in the union of A sub I. Okay. Now let's have here the theorem, the Heine-Borel Theorem. It states that we let here a closed and bounded interval, this one, this A, and we will let this script G here be a class of open intervals which covers A. So we have here our notation. A is contained in the union of G sub I. Then of course, the class of open intervals contains a finite subclass. Say for example, we have G sub I sub 1 up to G sub I sub M, which also covers A. So this is the notation for a covering of A. So A is contained in the union of finite subclass. Now take note here, for the Heine-Borel Theorem, our condition for a set A should be closed and bounded interval. Now if the set is neither closed nor bounded, we cannot use this theorem. So we cannot conclude if the class contains finite subclass in that case. So we cannot apply the Heine-Borel Theorem. So Heine-Borel Theorem can be applied rather for any closed and bounded interval that has open covers, which has open covering. So let us have an example of the set, rather the class of sets that has open covers. So let us try to consider this example. we let set A be equal to this closed and bounded interval. So this is closed and also it is bounded. Now let's have here an illustration. Here, say for example, we have here the closed, then we have here 2, 3, 4, 5. So we have our set here. Okay, now let us try to consider the class, the set of class. Say for example, A1 nato is 1, 3. Then A2 is 2, 4. A3 is 3, 5. Then open, it should be open intervals. A4 is say 4, 6. So let's have here A1. Let's plot here. So open A1 to A3. This is our A1. Then A2 is, we have 2, 2, 4. This is A2. Then A3 is 3, 5. And then A4 is, say we have 6 here. This is our A4. Now as you can see, if this is our, by the way, class, say up to that one pa, and then a class of sets, we can get the finite subcovering of this the class of sets. So we can therefore consider this one as our finite subclass. Take note how we can have many sets here. Pwede rin siya daghan diha. But our goal here is to get the finite subclass. So as you can see here, we can say that if we are going to get the union of A1, A2, A3, and A4, or let's denote that as this, where I is from 1 to 4, we can say that the set A is contained in the union of the finite subclass. So we have used here the Heine-Borel Theorem, that if the given set is closed and bounded interval, then the class of sets rather of open intervals here. This is, say for example, this is the class of sets of open intervals wherein A is contained in the union of A sub I, where I is from 1 to infinity. Infinite na siya, open covers. So this class of set covers the set A. Then we can get the finite subclass as this in our example. This is our finite subclass that covers, of course, the set A. Now, what about if the given set is not closed but bounded, or it is closed but then it is not bounded? It means the two important conditions are not satisfied. So what will happen? Okay, let's try to have this example. Let's have this example. Let's consider the open and bounded interval. This is unit interval 0, 1. Now take note again, we can use the Heine-Borel Theorem, or there exists a finite subclass of the given class of sets which covers the set if it is closed and bounded. But in our example here, we consider open, but then it is bounded. So, eto lang yung hindi na-satisfy. Okay, so let us try to observe if it contains a finite subclass that covers rather the unit interval A. So let us consider our subclass, our class of sets here. We have here script G, which is the set that contains the sets G sub n, where this is defined as our G sub n. So we have here 1 over n plus 2 up to 1 over n. So we have this one. So this is G1, this is G2, G3, and so on. Now, notice that script G na to contains open intervals that covers A. Because if we are to get the union of this one, union as illustrated in this figure here, if we are going to get the union of this set, it covers A. It covers A. But can we get the finite subclass? Notice that we have here the class of sets. And the class of sets, ni-approach siya dito sa 0. Paada lang siya. And notice that the intervals approach to 0. It will not pass through 0 here. It will only approach because we have here 1 over n. 1 over n plus 2. If n approaches infinity, of course, this approaches to 0. It only approaches to 0. So, can we get the finite subclass that covers finite subclass of G that covers A? In this case, we cannot get it because if we try to get the finite subclass, it will not cover A. As you can see, it only approaches to 0. But then if we will get up to infinity, class of sets, it will cover. But if we will get only the finite subclass, it cannot cover set A. Therefore, there is no finite subclass of this class which covers A in this example. Now let's try to have another example here. Take note the condition for the Heine-Borel Theorem, it must be closed and bounded. Now, if it is in this case, it is closed, but then it is not bounded. So, as you can see in this interval here, it is closed. We have here closed in 1. This is closed set, but it is not bounded set. Okay, our question now is, if we let this as our class of subsets of open intervals that covers A, can we get a finite subclass of G that covers the set A, where our A is closed and not bounded? So let's consider here an illustration. So our set is the closed and not bounded interval. We have here closed in 1 up to infinity. So we have here our G1. This is G1, G2, G3, and so on. So we have G1, G2, G3, G4, and so on. Now, as you can see in the given in the illustration, the class of sets of open intervals covers A. But then again, we cannot get the finite subclass of open intervals that covers A. Or else if we get it, if we try to get it, it will not cover our closed but not bounded set. So that's how important is the closed and bounded concepts for a given set if you want to get the finite subclass. That's all about the Heine-Borel Theorem.